I'm still having problems with my microphone connected to the PC. Okay. Could you just remind me a moment which we end our lecture last week? We just finished with this optical amplifier, I guess. Am I correct?
Yes, we were with dense wavelength division multiplexing, I think.
So I will share my screen and show you the slides. Yeah, you should see this one. And do you remember this slide also, or we should start from this WDM technique, I mean telecommunication topics for the fibers?
I think we were around page 48 or something like that would be, I think.
48. 47 was the last one.
Here, yeah, this one.
So we just finished with this one. Okay. So we need to change to the next. I have some questions regarding this exam. I need to just look at the schedule. Yeah. So the last lecture will be given 9th of June, and I think on this last lecture we can just have this final exam regarding the lecture, and also after the lecture part I will make the exam regarding, I mean the test regarding the laboratory. This is how we should perform it. Of course, the proper exam, I mean for the people who need to also pass the laser part, there will be something in a session 23rd of June, I guess. But this first, let's say, zero test regarding the lecture, the fiber part of the lecture, will be 9th of June, and it will be connected with the laboratory test. Yeah, exactly the same day. I mean, we will just make at first this test connected with the lecture, with this fiber part, and then after, because we'll have enough time to make two of them, the test regarding the laboratory will be much shorter. It will take something about 20 minutes or something like that. Yeah, so it will be that way, I think. Yeah, I will give you lecture presentations to ePortal, of course, in PDF version, so you can have them also. Yeah, just to prepare to the exam. Okay, so maybe or you have any other questions? If not, we can start with today's lecture. Yeah. So to continue our topic connected with this telecommunication, you already are familiar with this wavelength division multiplexing technique regarding transmitting the information with different channels at different wavelengths. So this is in fact the basis for the modern fiber telecommunication. So to multiplex or demultiplex such signals, we need to have some special devices, and the most common, the most popular device to just separate wavelength from one single fiber into different fibers, to just split the information to different receivers, for example, we need to use some device which is able to separate them, some kind of wavelength division multiplexer. And typically it is basing on such a construction, array of waveguide. It is made in planar fiber technique. I showed you these planar fibers. They are more or less similar to this printed circuit board for the electronics. For the optics, we can just produce such a structures. For example, Mach-Zehnder modulator is you cannot have this 2nd of June. I don't think, maybe we'll discuss it later, okay? Because right now, let's just have this this lecture continue, and we'll discuss about your tests later on, okay? After our lecture, we can just discuss it and just make some settlement. Okay, so it is made in this way, exactly the same like Mach-Zehnder modulator, for example, electro-optical modulator. It is also made in this planar fiber technique. Yeah, so here we have such a structure. We have one single input fiber, and the light from the fiber is producing some kind of a cone, and it is just coupled to the array of the waveguides. The length of each of the waveguide is carefully designed to have some certain phase differences on the output from such an array. As a result, different wavelengths, they are interfering constructively in different places in space, like it is shown on this picture. And of course, if you just simply put a fiber here, you will have a device which is able to just simply separate different wavelengths to the different fibers. Yeah, so this is the device to just let's say unbundle whole channels, whole transmitted at different wavelengths channels from one fiber into separate fibers for every channel. Yeah, so quite important device. Of course, it can just operate in two ways. If you just simply treat this ports as an input, and of course you need to keep this certain wavelength at certain fiber, it is able to just connect all the wavelengths from separate fibers into one common fiber. Yeah, so it is operating, it can operate as a multiplexer or the multiplexer. This is one extremely important device for this modern optical telecommunication. And the second one is so-called add-drop, optical add-drop multiplexer. And this configuration, this setup, as you can see, it is using two circulators and fiber Bragg grating. It is mainly for dropping just one single channel from our fiber and adding in the place of dropped channel at the same wavelength but with different information, for example. Yeah, so here we will have some, let's say, receiver at this certain wavelength, and here we will have some transmitter at this certain wavelength. Of course, the other wavelength I just go through such a construction without any change, and only one certain wavelength, the wavelength which is reflected by this fiber Bragg grating. So you can imagine we can also extract not one single channel, but if our fiber grating has wider band, it can be able to, for example, extract 2 or even 3 or in fact any amount of the channels from the fiber and keep other channels transmitting in the fiber. Yeah, so it is all the second, the most important element for these modern wavelength division multiplexing networks. So I don't remember if I told you about the capacity of these channels. I mean, of these WDM channels. Did we spoke something about the capacity? I mean, the amount of the information which is possible to transmit through one fiber using different channels. Regarding especially this slide showing the different channels amounts and the different channel spacings. Could you just remind me, because it is, quite important thing, especially regarding the next slide I intended to show you. And unfortunately, in this week, I had two other lectures. Okay. Because I have some mix in my head because I had two additional lectures in this week, and all of them were around these channels, WDM channels capacities. So I don't remember precisely which information I gave to you regarding this one. So for sure, what are the bases about this WDM technique? I mean, the increasing the fiber capacity. Yeah? So we are transmitting the information at different wavelength, different channels, quite similar to the, for example, FM radio. Yeah, we have some band of the frequencies. What's going on here? Okay. I should just for a moment turn on the presentation for this one. Yeah. Yeah, so this slide also tells you something about it, but this one is the most important, in fact. Yeah, we are putting a lot of different wavelengths to the fiber, and in our fiber we are putting all of them one next to another, but every wavelength, every channel has some certain spectral width. Yeah, it isn't one single wavelength, in fact. If we have, for example, wavelength domain, we have some lambda 1, our channel number 1. Yeah, this will be the channel number 2. How dense could we just put the channels to one fiber? How close they can be together? What do you think? What are the limits of closing the channels to each other? So how many channels can we have regarding, for example, third telecommunication window? Do you have idea what is the limit for us for closing the channels? So maybe some additional question. What will happen? We can just consider the one single channel. So we have a laser at some certain wavelength. Yeah, it is emitting the wavelength. This is the spectra of the laser. What will happen if we just start to modulate the amplitude of such a signal? What will be changed to the spectra of this signal? It will remain, I mean, the same, like without any modulation, or it will change? How do you think? What will happen?
Some broadening occurs.
Yeah, we will see some broadening, and the broadening, what will determine how broad we will have the spectra of this signal? Yeah, so we'll have some broadening of the signal, yes. So our delta lambda. What will define this delta lambda for us? For such a case, we are modulating. I think you had something connected with this topic. This telecommunication lecture and laboratory, in fact, you met, I think you had it a year ago. If we are, for example, are using AM modulation, AM means amplitude modulation, the principle will be quite simple. If we are modulating with the signal which has some certain frequency range, the spectra from 0, for example, to, let's say, 1 gigahertz, yeah, so our modulating signal has such a range of the frequencies. Yeah, so we are modulating with the maximum frequency of 1 gigahertz. It means our line, our carrier wavelength will be also broadened by exactly the same frequency. Exactly the same means we will have some wavelength and spectral width of such a signal will be 2 gigahertz in our case, because this broadening is by 1 gigahertz to the right, to the higher frequencies, and to the lower. Yeah, so it will give us some lambda plus minus f max, or in fact we should give here the ni, the frequency of our light beam propagating in the fiber. Yeah, it will be broadened by the range of the frequencies which are modulating our signal, our wave. It means we cannot close channels more than spectral width of one single channel. Yeah, spectral width of one single channel is given, in fact, by the maximum frequency we are modulating the channel. And regarding this topic, we can have different, let's say, different filling ratio of our whole band of the wavelength we are using. Typically, at first, the systems were using so-called coarse WDM system, where channel spacing, it was 20 nanometers, and as you can see in the frequency domain, it is something close to 3.5 terahertz. So it means we shouldn't care about this bandwidth of one single channel. Yeah, the channels are way away from each other, so they are well separated. But if we will go to WDM technique, I mean this modern telecommunication technique, where we have 40, 80, or even 160 channels, they have small distance because the bandwidth of this third telecommunication window is limited. Yeah, so if we have, for example, 40 WDM channels, the spacing in the wavelength domain is 0.8 nanometers, but in the frequency domain it means it is 100 gigahertz. Quite a big, but regarding the thing I just told you previously, the maximum capacity for the bandwidth regarding the modulation will be 50 gigahertz, yeah, for such a system. 50 gigahertz is the maximum frequency of these modulating signals, yeah, for 50 gigahertz spacing, 0.4, so it will give us 80 channels in our WDM system. It will be 25 gigahertz and so on, yeah, so regarding these issues, you can imagine we are filling almost all available bandwidth with the information, with this modulation signals. Yeah, so the system needs to be considered as some balance between the amount of the optical channels and the frequency of the modulation or the bit rate of one single channel. Yeah, for this 10 gigahertz, 100 gigahertz spacing, 40 gigabits per second will be quite possible. Yeah, in fact, it is dedicated for such a systems. But if our optical channel spacing will be smaller, we will start to have some limit regarding the maximum frequency we can just modulate the signal to avoid crosstalks between the channels. Yeah, so some balance is needed to be taken between the price of the electronics. Yeah, the fastest the electronics is, of course, the more expensive. But from the other side, the smallest distances of these optical channels also increases the cost of such a system a lot. Yeah, so for such a system, we'll have a lot of optical channels. Not so fastly modulated, but the price for the optics will be high, price for the electronics for such a system will be low. Yeah, so some balance is needed to be taken. Oh, why it just stopped? Doesn't matter. In fact, we just finished this slide and we can go back to our main slides regarding this WDM technique, because the next slide will show you additional issues connected with this fiber and system capacities regarding the spacing between the channel, the one single channel capacity, multi-channel, you can see, yeah, so increase in the amount of the information of the capacity if they started to develop systems using multiple optical channels versus one single channel transmission, but also additional parameter and additional development is made in so-called spectral efficiency. Yeah. Right before I just told you, we can tell we have 1 bit per second per 1 hertz of the bandwidth used. It isn't fully true because, you know, depending on the modulation scheme and other things, we can have this spectral efficiency quite different. And in fact, for this, let's say, old telecommunication systems, you can see we have this spectral efficiency much lower, and the spectrum used for 1 bit transmission was quite big. Right now, we are over the possibility to have more than 10 bits per 1 hertz of this bandwidth use, and this approach requires to use different modulations different modulation types than simple AM modulation. Yeah, if we are using AM modulation, this transition from this bandwidth of the modulating signal to the bandwidth of the whole signal after modulation is quite simple, but we can use different approaches. Some QAM modulation, so this will add additionally not only the amplitude is modulated, but also a phase of this optical signal is modulated. Additionally, we can code information not with zeros and ones, but we can use, for example, 4-level amplitude modulation in such a system. Yeah, so we'll have 4-level modulation and additionally 4-level phase modulation in such a thing. So one time slot for such a modulated signal will in fact code 4 bits of the information. Yeah, so it will give us more or less in some approximation this spectral efficiency equal to 4 bits per 1 hertz of the bandwidth, and so on. Of course, these modulation schemes and way how to do it to increase this spectral efficiency, they are quite sophisticated, so we don't need to speak about them here. Yeah, but you should have in your mind that modulation format also allows to increase the capacity for such systems, and you can see right now the capacity of one single fiber. It is important. Yeah, this is the capacity, the amount of the information transmitted through one single fibers, and right now it is exceeding way 10 terabits per second. It is data which ends at 2010. Right now the numbers are even higher. Yeah, so the systems are able to transmit, let's say, 30 terabits per second. Yeah, these are something over, I don't remember the exact number, 50 terabits per second for one fiber is something close to the record value right now. Yeah, so huge amount of the information for one single fiber, and you can imagine in one fiber cable we have couple of fibers or couple tens of fibers. Yeah, so right now the possibilities for and capacities for such a systems are huge. Regarding this modern optical fiber telecommunication systems, also additional property of such a system is important. I mean, optical transparency of such a system. We have a system which don't have conversion from the optical signal into electrical signal and vice versa in any place of our network. The only conversion from electrical to optical and optical to electrical is at transmitter and receiver, and nowhere else. Yeah, the other parts, other components of the network, they are fully optically transparent. It means they are using the optical amplifiers for regenerating the signals. They are using optical switches to just change a routing. They are using also optical, because right now it is also possible to even convert the signal from one lambda, one wavelength into another wavelength in completely optical way. Yeah, using some nonlinear effects and other things, it is possible to convert the signal at one wavelength into another wavelength. Yeah, quite difficult to imagine how it can be done, but it is possible, and right now the systems are also using such a properties. And of course, such a optical transparent network can be in fact extremely large. You can imagine this one can be in Poland, and receiver can be in United States, and all the transmission is made by the photons through whole our network, starting from our transmitter up to the receiver somewhere in New York, for example. Of course, it isn't possible for one single photon, because the photon will be amplified somewhere it will be attenuated, but in fact to the receiver we have a guarantee that not maybe the transmitter photon will reach the receiver, but some childs of this transmitted photon they will receive our receiver. Child, I mean something which is because of some stimulated emission, yeah, so it is also still in phase with our, let's say, starting photon. So all the transmission is made optically. Before this era of transparent optical networks, to regenerate the signal, for example, to amplify, you can imagine we should just put some, yeah, so we have a lot of lambdas, we have some multiplexer, one single fiber. To regenerate such a signal which has a lot of lambdas, we need to add the amplifier, split them to separate wavelength. Every wavelength needs to be detected, then amplified electronically, and transmitted, I mean some transmitter, and next WDM multiplexer, and put to the fiber for another 100 kilometers, and the situation will be, of course, repeated. Yeah, so before era of optical amplifiers and optical transparent networks, the systems, they could look only like this, these WDM systems. Right now, because of these optical amplifiers and other devices, we are able to totally take out the electronics from the path of the information stream in our network. The whole things are made optically. And something connected with this previous slide and previous topic, signal regeneration. You know the first type of regeneration already, 1R regeneration. This is re-amplifying of such a signal. So it is quite simple, yeah. The signal is just attenuated in a fiber, so the amplitude of this signal is dropping through transmission through the fiber. After some certain distance, we need to amplify it, so we have optical amplifier, quite simple thing. But also the second type of regeneration is possible: re-amplification and reshaping. Reshaping means, here you can see a difference. Yeah, this is only re-amplification. Yeah, so but all the distortions connected with some nonlinear effects, some noise in this signal, they will remain. Yeah, so after couple amplifiers, they will be, of course, accumulated. So after some distance of the transmission and some amount of the optical amplifiers in our transmission line, they will be so big that the eye in this eye diagram will be closed, and the transmission will be not possible anymore, yeah, for longer distance. So the next step, the next evolution of such a systems is also reshaping. It means clearing the zeros and ones, removing all the noise from the signal, yeah, and equaling the levels of every bit to be constant, yeah. So this is the reshaping. But still sometimes the jitter remains in this signal. So the 3R system, this, let's say, the most complete regeneration systems, they have also so-called retiming of the signals. So we, as you can see, also are repairing the edges in this eye diagram. It means we are improving, repairing the timing of every bit transmitted through the systems, yeah. And even this 3R regeneration right now is possible in fully optical way, yeah. Before, of course, it can be easily done using the electronics. You can imagine this reshaping, for example, detect, determine if it is 0 or 1, and then transmit it once again. So we will have exactly regenerated the levels. Yeah, retiming, make the same with this time. Yeah, so detect the 0 or 1 and then transmit it, but using own clock with the constant period, not varying during the transmission. But it is quite easy to make it electronically, but optically it isn't so simple, but it is possible. And right now the systems are also using this 3R full optical regeneration. also including retiming and reshaping, not only amplifiers. Just to, I think, finish these topics connected with these fibers and fiber optical telecommunication, something just to help you maybe understand what's happening on this exercise connected with this OTDR, because just to develop and perform some measurements in the networks, of course, some tools are necessary. At first, I will show you quite basic tools like optical time domain reflectometer. It is working more or less like a radar, so we are just putting a pulse into the fiber. It is transmitted through the fiber, and every event in such a fiber which just partially reflects a light will give us some return which is detected by photodetector, APD typically, so avalanche photodiode, just to have high sensitivity of such a system. Also, the fibers themselves, they are producing some backscattered signal due to this Rayleigh scattering. Yeah, so on the screen of this OTDR, you will see very typical trace. You are observing it on this laboratory, showing you the fusion splices, some connectors, also some losses because of bending of a fiber or even cracking the fiber. Yeah, so everything is possible. We can see a distance on such a OTDR trace, and we can localize, for example, crack or just bend on the fiber where it is happening, and just send some guy to improve or repair such a event on the fiber. Yeah, so we have full diagnosis of transmission line, and it can be done even from one side of such a transmission line, with the exception of the same fibers are used in the whole transmission line. You are on the laboratory, you are also meeting with a problem connected with the fiber which has slightly different this backscattering coefficient. So in such a case, you can see some, let's say, amplification in this OTDR trace, and this amplification is of course made by this higher backscattering coefficient for such a different fiber. Yeah, so there are also ways how to calculate the attenuation and losses of such a splices and connectors on such a different fibers, but they are requiring to have access from both sides of a fiber. Okay, so this is quite simple diagnostics of optical networks. So right now I will show you how the, let's say, more sophisticated diagnostics of the fiber systems is performed. Here you have 4 quite typical estimators of the optical link quality, because you know the attenuation is the one factor which is in fact necessary to just determine if the system will be able to operate or not. Yeah, the amount of the power you will be able to receive at the receiver for some certain system. If you want to develop or evaluate performance of a system regarding some dynamical system signals transmitting some data with some certain bit, I mean with some speed of the transmission, some bits per second, megabits, gigabits, or terabits per second. We need to have another types of the measurements, and of course almost all of them are made on the dynamical signals. The first one, which is in fact for static systems signals also possible, is determination of so-called optical signal to noise ratio, OSNR. You can see here some practical pictures showing you how to measure this OTDR. In fact, on the laboratory, if you are measuring this erbium dot fiber amplifier, you can see a spectra of the noise of an amplifier, and of course the peak of the laser, the power of this peak you are measuring, yeah, but you can easily determine signal to noise ratio, optical signal to noise ratio for such a system, just measuring the noise level and the peak power, and this is how we are measuring this OSNR. It is quite fast, let's say, factor which allows to tell us the maximum, for example, maximum transmission rate able to be received for such a system regarding some sensitivity of the receiver and some power in the transmitter. But unfortunately, of course, it is static measurement, so we cannot estimate any limits connected with some dispersion effects or some nonlinear effects which can appear in such a system. Yeah, so this one allows us to just estimate maximum transmission rates and bit error rates quite efficiently, but considering good designed system without any dispersion or nonlinear effects. In the case where we can expect some dispersion or nonlinear effects, some dynamical measurement need to be taken, and diagram I think is one of the most obvious methods how to determine the property of a transmission through some link. We are measuring two things. First measurement always is so-called back-to-back measurement. So we are just simply connecting transmitter with the receiver, and we are observing the properties of the transmitter and receiver themselves without any transmission line between them. So you can clearly see, for example, for this picture, it was, I don't remember the value, but it was taken, if I remember correctly, for, here I have 20 picoseconds per division. So the bit time was 100 picoseconds. So it was 10 gigabits per second system. Yeah, this was 10 gigabits per second system. I just made this measurement a couple years ago in Italy, in Pisa. I was on some, let's say, short-term cooperation with some Italian university, and we were measuring such a systems using at first back-to-back measurement. So yeah, so we were connecting our transmitter with the receiver just to see the quality of them, and then after having this back-to-back to just compare and to see the degradation of the signal, you just transmit the whole signal through the transmission line. It was in this case it was 60 kilometers of the fiber, having built in ring configuration, such a simulation of a network in ring configuration using semiconductor optical amplifiers. So they had some problems with cross-gain modulation, for example, for such a systems. They were quite sensitive to dynamical add and dropping the channels transmitted in such a system. So you can see the performance of such a system without any dynamical add dropping, and with add dropping you can see the noise margin becomes much smaller. The noise in this system increases if you start to change the amount of the channel transmitted in such a system, and all the things can be quite easy observed on this eye diagram. Also regarding some issues regarding with this, you can see dispersion effects. Yeah, this not flat tops of these bits, but the hills here, they are mainly because of the dispersion, because our network wasn't dispersion compensated. It was only 60 kilometers, so the dispersion management wasn't so important in this network, but it appears on the eye diagram quite easily. The next estimator of the network quality can be Q factor. Q factor is calculated with the OSNR, optical signal to noise ratio, and this is the way how you can estimate maximum bit rate and maximum bit error rate having this OSNR. Using this Q factor, it is quite easy to calculate it. Another measurement, so-called effective or optical signal to noise ratio. Effective is considering also received input power. So you are investigating this optical signal to noise ratio, but you are changing the received power, I mean power at the receiver state, and you are measuring bit error rate for such a received input power. And last, the most complete characterization of this of the optical network, bit error rate measurement, but typically it is measured versus received power or versus optical signal to noise ratio at receiver side. For received power is the most common method, and here you have two graphs for the same network I showed you with these eye diagrams. Yeah, using 16 channels, we are measuring the bit error rate for one single channel, but having different configuration of the amplifiers in such a network, and additionally adding and dropping dynamically the channels for these different amplifier configurations in such a network. So how did you perform such a measurement? At first, typically we are taking back-to-back measurements. So we are just simply connecting transmitter to receiver, and we are measuring bit error rate for a certain bit rate transmission. It was 10 gigabit per second. Yeah, you are measuring bit error rate for changing the power at the receiver side, decreasing the power on the receiver, strictly speaking, using variable attenuator. Yeah, so you can see for high input powers, this bit error rate is even better than 10 to the minus 10. Yeah, it means every 10 to the power of 10 bits is transmitted in wrong way. Yeah, so errors appears once per 10 billion bits transmitted. Yeah, bit error rate equal to 10 to the minus 9, of course, means one wrong bit per 1 billion bits transmitted, and so on. So you can see if we are decreasing the received power, of course, bit error rate is also increasing, but it's becoming worse and worse. Yeah. For example, here for bit error rate equal to minus 3, it will mean every 1,000 bits of the transmitted information, one of them will be wrong. Of course, statistically. Yeah, so we are making such a back-to-back measurement, and after we are putting the same signal to our transmission network, we are receiving power from using the same receiver, of course, and we are checking what will be the dependence between the received power and bit error rate. You can see, to have, for example, the same bit error rate, we need to have slightly higher power at the receiver. And you can see it is different for different pumping configurations, I mean different amplifier configurations. It will also show you why this booster configuration is better than pre-amplifier, because look, triangles are the configuration where the amplifiers in the network was used as a pre-amplifiers. Circles are for amplifiers used as a booster amplifiers, and squares are for amplifiers used as inline amplifiers, exactly in the middle between transmitter and receiver. And you can see for having the same bit error rate, 10 to the minus 9, for the configuration of the preamplifier, we need to receive much higher power, minus 15 dBm, than for the configuration with the boosters. For boosters, the power slightly higher than minus 18 dBms is enough. Yeah? So in this way, we are calculating so-called power penalty. Yeah? How many dBs received power should be higher to maintain the same bit error rate than you have for back-to-back measurement, I mean without any network between transmitter and receiver. So this is the way how to measure such a parameter. And the schematic of this network, it was ring network, 60 kilometers of the fibers. Yeah, all the structure for such a network was circle, and one node just emulating, adding and dropping the signals, and also the signal which we were treating as a probe. So this signal was transmitted, and bit error rate for this signal was investigated in such a configuration you can see here. Yeah, I just already told you power penalty determined for regarding different placement of these optical amplifiers in our network, and the same determined for additionally adding and dropping signals. So I told you these semiconductor amplifiers, they are quite sensitive to the power. Their gain dynamic is quite high. So in such a case, this inline amplifier is the best configuration regarding this power penalty. Not booster, not preamp amplifier, but for such a configuration where the amount of the channels can change dynamically in such a system, this one is the best regarding this bit error rate and power penalty. Okay, so maybe about the telecommunication, it could be enough. If you have any questions regarding this telecommunication, you can ask now, or just write down somewhere and ask after the lecture, because right now we will go to completely different topic regarding the fibers. I mean high power fiber lasers, amplifiers, and high power fiber stuff, in fact. So I hope Grzegorz didn't tell you anything about high power fiber lasers or amplifiers, just to avoid some repeating of the information. But you for sure know about the solid state lasers, yeah? You know what the solid state lasers are? You are familiar with them? Okay, silence means agreement. So, more or less, okay. So I will treat more than less. You are familiar with them? Yeah, the basic thing, we have some solid state, some media, which is typically in form of some crystal, for example, so-called YAG crystal, and it is doped by some dopants, for example, neodymium ions, yeah, and these dopants are active media for our laser, so we are just simply adding two mirrors, and we have such a structure which is the laser. Typically, solid state lasers are optically pumped, so we are putting some light from the side to our gain media to excite this neodymium or different or other ions to these upper states, and to enable this stimulated emission inside of such a media, allowing it to just become active media of the laser. Yeah, so it is more or less like this. And of course, solid state lasers, in fact, the first laser which was operating and invented was solid state lasers. Do you know what type of a laser was the first one? Do you remember? Ruby laser. Yeah, ruby laser, exactly. And this was solid state laser, yeah, the ruby crystal ended with two mirrors and pumped by some flash lamp is just emitting red radiation. Yeah, so this was the first laser ever operated. Yeah, so as you can see, it is well-known technique developed from the beginning of the laser technique. In fact, they have quite good power scaling, because power scaling for such a laser is only about scaling of the pumping power. Typically right now these lasers are pumped with semiconductor lasers, of course, but there are some problems. The biggest problems, especially for high power, are problems connected with the cooling of such a lasers. There are some solutions for the cooling, like let's say, for example, ring lasers or other configurations. But the ring lasers, this is, let's say, the best solution for the cooling. And beam quality at high power also, because, you know, if you have solid state, I mean the crystal, and we have some laser beam which is propagating in this crystal, and this laser beam has extreme intensity. Of course, the temperature of the crystal isn't uniform. Yeah, in the middle of the crystal, for example, the temperature is higher than on the sides, because the crystal is cooled from the sides. So not uniform temperature distribution of such a crystal makes so-called thermal lensing effect appearing. Yeah, thermal lensing. So it means in our resonator, our laser resonator, additional length can appear, changing the geometry of such a resonator. And you know, the geometry of the resonator determines also if it is able to just operate at Gaussian mode or start to emit also higher order modes of the radiation. You know, from the laboratory, the Gaussian mode, Gaussian beam, is the best quality possible beam. So regarding high power applications, we want to have as good beam quality as possible. And this thermal lensing inside of such a media makes for high power to having and getting Gaussian beam quality, or at least close to Gaussian beam quality, quite difficult or even impossible at higher powers. For fibers, if you just think about single mode fiber, you know, in single mode fiber you have this Gaussian beam propagated by default. In single mode fiber, nothing else than Gaussian beam can be propagating. So from the fiber lasers, if they are single mode, we have this Gaussian beam quality by design, in fact. Yeah. So this is the advantage of such a fiber laser. Also, fibers, regarding the dimensions, they are quite similar to solid state, but in fact the gain media is long and quite thin. So cooling such a media is much easier than cooling, let's say, some thick rod, which can be gain media for solid state laser. There are also some, let's say, disadvantages for fiber lasers. Regarding these small core diameters, we have low pulse energy possible for such a systems, and the non-linearities, they can also quite fastly appear in such a lasers. But sometimes we can use these non-linearities at our advantage. So sometimes it is advantage, sometimes it can be disadvantage, depending on the application. And typical applications of such a high power lasers, not only the fiber, but also, of course, the solid state lasers, but fiber lasers are quite good fitting to these applications you can see on the screen right now. Starting from the telecommunication, you can ask why I'm talking about the telecommunication right now, because some quite specific domain of the telecommunication requires using high power fiber amplifiers, for example, especially in cable television. You can imagine it. The network configuration is a tree configuration. Yeah, we have one transmitter and a lot of receivers. So we need to just split a signal from one transmitter into many receivers. So it requires to have quite high power at the transmitter side just to be enough for every receiver to be detected. So high power amplifiers are quite useful for such application. Also so-called free space optocommunication. For example, intra-satellite telecommunication at long distances requires to use high power laser beams to have reasonable distance of the transmission, because in space, you know, the beams are diverging. Yeah, even the Gaussian beam is diverging, so receiver isn't able to receive all the power emitted by the transmitter, but it is receiving only small portion of this emitted beam, small area of this beam. So the power transmitted even in space is needed to be quite high. Another application, laser machining. In fact, you just met with this on the laboratory, because the system you were using in this first round of the exercises for this marking was the fiber laser. Yeah, rangefinders and other applications connected with this, let's say, pulsing and sending pulse into the space and receiving the signal. So you can imagine also high pulses, high energy pulses are quite important for such a thing. And other applications, medicine, because at this wavelength, which are useful for the medicine, in fact, fiber lasers are dominating regarding the source of such a radiation. For example, extremely short pulse lasers, mode-locked lasers, are typically the lasers which are operating, which are fiber lasers. Also, lasers used for surgery, they are operating in 2 micron wavelengths, so thulium or holmium fiber lasers also are quite useful, quite nice for such applications. So going to this high power fiber amplifiers and lasers, the whole thing is connected with the pumping power. Exactly the same like for the solid state lasers. The only difference is we need to put this high pumping power into the fiber, and regarding the sizes, it is extremely difficult, especially if you regard high powers. Yeah, because as a pumping sources for fiber lasers, only semiconductor lasers are used. And semiconductor laser, if you just think about semiconductor laser, there is one huge disadvantage of such a laser: the beam quality. Yeah. If I'm giving the lecture connected with the laser technique, sometimes I'm even asking why solid state lasers are operating in such a way. Look, I can also ask you here. Yeah, we have solid state laser. We have a rod which is just doped with, let's say, neodymium ions. We have a mirror here and here, and we are putting some semiconductor lasers from the side just to pump optically our rod to excite these neodymium ions here in our rod, and we are receiving the radiation from this direction. Yeah, at 1.064 for the micron for this neodymium, and pumping radiation for such a neodymium laser is 808 nanometers. So how do you think? Why anybody is using such a configuration? You can imagine the efficiency of such a laser at its best for neodymium laser, it will be 50%. Yeah. So to have, let's say, 100 watts of output power, we need to use at least 200 watts of the power from these semiconductor lasers on the optical power. So why we are using such a thing? Pure waste of the energy, in fact. How do you think?
So can we here use the frequency doubling to achieve 500 nanometers wave and with higher energy or something?
No, we cannot. Yeah, we can of course add this second harmonic generation crystal here, for example, KTP crystal. Yeah, so as a result, we will have 532 nanometer wavelength, so it will be green radiation, but we will decrease the power even more, yeah, because the efficiency of such a process also is not so high. So not the wavelength is the answer for this. In fact, we can just make a semiconductor laser operating at 1.064 nanometers, and we can also double the frequency for such a radiation. We don't need to use this solid state laser to make it. So not the wavelength is the answer for that question.
Maybe the quality of the beam is better.
Yeah, it's way better, especially regarding high power lasers. Yeah, if you consider, for example, 100 watt semiconductor laser, it is in fact some matrix of small lasers placed more or less like this, yeah, in some, let's say, sandwich, couple parallel emitters, couple layers of these emitters. Yeah, so the quality of such a beam is not really better than quality of the beam going out from the LED, for example, light emitting diode, or even from, let's say, light bulb. No, light bulb maybe not, but LEDs can have quite similar beam quality to such a thing. Yeah. So since you have such a beam, you have extremely poor beam quality. If you just transfer it using solid state laser, for example, to the different wavelength, it isn't so important because we can change the wavelength of the pumping laser and output from our solid state laser, changing the dopants, for example. And we'll have, for example, 50 watts of power, but in beam which has the quality quite close to Gaussian quality, we have much better possibility to use such a laser to make something. I can give you some examples. The numbers will be slightly not correct, I guess, but they will tell you what it's all about. For such a beam quality, using some certain lens, we can focus such a beam to, let's say, 0.5 millimeter of diameter, and for our output Gaussian beam, we can just focus the same, beam with this Gaussian quality using the same lens. It is important also, yeah? So the emitter has exactly the same size, and we are focusing the beam from semiconductor laser and from our solid state laser using exactly the same lens. It means the focal distance is exactly the same, and this so-called Rayleigh length distance is exactly the same for both cases, yeah? So for this pure beam quality, we'll have focal spot 0.5 millimeter. For this Gaussian beam, we'll have, let's say, 10 micrometers. The difference in, let's say, dimension will be 50 times, yeah? 50 times smaller, but regarding, am I correct? 50? Yeah. It is 500 micrometers, and here we have 10 micrometers. Regarding the area, it will be even higher. And if you consider the interaction between laser beam and some matter, some object, not the power itself is important, but the power density. You can imagine even half of the power of this beam, but focused at much smaller spot, will give you much higher result, much higher interaction between the laser radiation and this object. Yeah. So the result of this will be, in fact, significant. And here we can have no interaction. For example, if you want to make some marking on the metal and have half of a millimeter of beam diameter, you should use, I don't remember, but some kilowatts of the optical power to even scratch this metal. Yeah. So this is why it is so important regarding these high power applications to have high beam quality. So semiconductors, they have extremely poor beam quality, and also it is connected. You cannot pigtail such a poor quality light source with single mode fiber. Yeah? Single mode fiber, if you have small core diameter, to efficiently put the light from the light source into the single mode fiber, you need to have Gaussian beam. If you have worse quality of the beam, you will have low efficiency of such a coupling. And if you have a lot of emitters here, you could not put the almost non-light to such a single mode core. So you can already see some, let's say, obstacles to have high power lasers and high power pumpings, because I told you the beam quality is always necessary for such applications. And from the other, so we need to use single mode fibers, and from the other side we need to also use some high power lasers to pump, but unfortunately high power lasers cannot be coupled to single mode fiber. Yeah, so typical amplifiers, you met erbium doped fiber amplifier on the laboratory, they are using this single mode fiber scheme for operation. Yeah, they are using single mode fibers, and active fiber, the dopants are in the core of such a fiber. Yeah, but we have this limit connected with this pumping power. Yeah, only low power semiconductor lasers are able to just efficiently launch pigtail to this single mode core. To enable high power pumping for such a systems, high power systems, another type of a fiber was developed, so-called double clad fiber. Yeah, if you draw refractive index profile for such a fiber, it has in fact 3 layers. The core, of course, has the highest refractive index. The first cladding has slightly smaller one. Yeah, so this structure, I mean this N1 and N2 can be exactly the same like for single mode fiber, but we have additional layer here, this external. It has even lower refractive index, and in such a approach we can propagate a signal through single mode core. Yeah, so we'll have excellent beam quality on the laser or amplifier output, but from the other side we are able to launch much more pumping power to the multi-mode core. I mean multi-mode propagating first cladding. Yeah, this first cladding acts like a multi-mode core for pumping radiation. Yeah, so quite simple and in fact quite obvious solution. Not so simple to produce, to manufacture, but the idea is quite simple behind. And of course you can imagine if you have, for example, this first cladding diameter equal to typical value 125 microns. So for such a structure we can put, for example, couple hundreds of watts, let's say, I don't remember record values, but you can buy lasers, let's say from the stock, which has 100 watts of optical power, and you can couple 6 such lasers to such a cladding. Yeah, so for such a 125 micron cladding, you can put 600 watts of optical power, basing on the stock components. So you can buy them and use and made such amplifier or laser. And if you want to pump in this scheme, let's say 1 watt will be the limit of the pumping power for you. Yeah, so you can see a difference. 1 watt of the pumping power and 600 watts for this dimension. You can imagine we can make much thicker this first cladding, and we'll be able to put even more pumping power for such a fiber. The second thing connected with this double clad fiber is, let's say, geometry in the cross section. Yeah. First approach, of course, we should use this standard geometry. I mean, core cladding and first cladding and second cladding, they are in circular symmetry, but unfortunately, if you just remember how the beam can be propagated, I mean, the rays can be propagating in such a fiber, they can produce such a modes also, which aren't able to cross the core of such a fiber. So these rays, they will be wasted. Yeah, they wouldn't take a part in the pumping, because you know the active part is only core of such a fiber. Yeah, only in core we have these dopants. So such a geometry is useless, in fact, because it will have much smaller absorption than we need, and a lot of power will be just wasted. So other geometries are used for such a fibers, such a double clad fibers. This one is the most popular. This hexagonal structure, I mean, this first cladding is hexagonal, not circular, but hexagonal. One company a couple years ago, they were forcing this star configuration, but they stopped to make any active double clad fiber. So I think they decided their idea wasn't so good. Also, this D-shape is quite popular. Yeah, everything which just disturbs this ideal circular symmetry in such a fiber will be good to improve efficiency of such a pumping. Also, some asymmetrically placed core will help. And here you have some data of typical absorption versus different shapes of this first cladding. You can see the shape also matters for such a case. But as I told you, this hexagonal structure is the most popular one. Additionally, this first cladding should have high numerical aperture. The reason is exactly the same. If you have higher numerical aperture, you will be able to put more pumping power from the semiconductor lasers to such a structure. Yeah, so typically this secondary cladding is made not of glass, but with some low refractive index polymer. Yeah, so this coating of the fiber, this secondary cladding is made of polymer typically. So it needs to be polymer with good optical quality. You remember, if the light is propagating in the fiber, some small part of this light is also propagating in the cladding. So if you have a polymer as a cladding, you need to have a cladding with quite good optical quality, just to avoid losses and attenuation of such a signal, especially if you think about high power. Yeah, if you are transmitting extremely high power, 600 watts for such a fiber, the polymer need to be extremely pure, just to avoid any heating up or even burning such a cladding. Okay, so next point is how to introduce the light, pumping light and our signal light to such a double core fiber. So couple different bulk optics schemes, of course, they were developed at first, yeah, especially regarding high powers applied to these structures. So bulk optics, it was the first approach and the safest one regarding, you know, the heating and other issues which can appear if you are using high optical power with extremely small areas. Yeah? Even this 100 micron first cladding for such a fiber, if you consider a couple hundreds watts on such a small area, it will heat up if you just put anything absorbing on such a area. So the quality and cleanness of all the components is also important. So first approaches, they were made using bulk optics, quite typical one. End pumping of such a fiber. So we have something which is called dichroic mirror. We have signal laser, some lenses, foaming beam, Gaussian beam, which is just coupled to the core of a fiber, and second beam which is formed by another lens, and it is focused on this first cladding, and this is the pumping radiation. So you can see it is pretty complicated mechanically. So this type of a pumping was present only, in fact, in some, let's say, scientific researchers, but cannot be used in industrial applications because of its sensitivity. You can imagine the core of a fiber is couple micron. The whole thing is operating at extremely high power levels, so every temperature change and other things requires to align the system. So they are delicate, sensitive to the mechanical misalignment and temperature and other things. Other approach can be so-called side pumping using some V-grooves or other structures just made on the fibers. Yeah, everything which allows to just separately introduce the signal to the core and pumping radiation to the cladding, they were okay, but all of them were basing on bulk optics, so they weren't practical regarding industrial applications. So regarding developing of this high power technology, all first focus was put on these so-called all-in fiber techniques. All-in fiber techniques, the technique for coupling the pumping radiation and signal radiation into such a double clad fiber in completely fiber way. Yeah, so the first approach could be something like that. We are just simply putting the fiber from the side, connecting these pumping fibers in some way to this double clad fiber, and it should work more or less. But of course, on the paper it looks nice. In reality, it is extremely difficult regarding the connecting the fibers. Yeah. Anything connected with some polymers or glue is impossible to be applied close to these areas where we have high power. So everything connected with these pumping fibers, they cannot use any glue to connect the elements together and other things. So the development was taken mostly about this properly designing and producing so-called fiber combiners. And here you can see two, let's say, pictures from patents. Both of them are right now, let's say, they are visible because the patents are guaranteed by and they have the companies which are just made these patents, they have them right now. Yeah, this was patent pending, but right now it is the patent is given already. Yeah, the idea is quite simple. Just take a bundle of the fibers, just taper them and splice to the double clad fiber, and that's all. Yeah, so pretty simple solution. Or you can make such a connecting, take couple fibers with smaller diameter, of course form a bundle also, but without any tapering, just splice to the higher diameter double clapped fiber. Yeah, quite simple solution, but of course all the things, all the technology is in the details of producing of such a structures. So they appeared on the market, I don't remember, in 2005. There was only just some beginning of such a components available. They were operating at low optical powers, 2 watts per pumping input or something like that. Yeah, so not so impressive. And of course, the development was made during these days, and right now you can buy such a fiber combiner for the powers even higher than 100 watts per one pumping input. Here you have another example of such a structure, and here you have, let's say, holy grail for this high power technology, because it was invented by the IPG company. This is the company which is regarding the high power fiber lasers market. In fact, they are dominating in this market. Even in the year 2004, 2003, all the companies who are making high power fiber amplifiers, they had, for example, output power of the amplifier equal to 2 watts, maybe 5 watts. IPG, these days, they had the amplifiers which gave output power higher than 10 or even 20 watts. And of course, everybody in the market, they were considering how they are able to make such a high output power, having exactly the same technology like they had. And after appearing of this patent, yeah, they found IPG solution for such a technical issue. They are coupling, they have long double clad active fiber, and they are adding such a side pump structure to this active fiber after every distance of this active fiber. Yeah, so they are able to put a lot of pumping radiation into active fiber using this approach. Of course, they kept this approach in a secret, and after having a patent, everybody could just see how they get such a high powers. And right now, they still are leading in this at this market, because they have more or less 10 times more power at one single laser than other companies, because of the patents they have for such a structure, such a lasers. Yeah, the wavelength and dopants exactly the same like you have in solid state lasers. We can use more or less the same dopants. You know one of them already, erbium, quite popular for the telecommunication. But for technological applications, we have a king, ytterbium. Ytterbium, this is the element which has emission line close to 1 micron. So you can see more or less the same like the neodymium, but has much more strict energy structure, allowing to produce extremely efficient lasers. Look at the energy diagram for these ytterbium ions, which are used as dopants for these high power applications. In fact, it has only couple energy levels. It has nothing appearing here. Oh, what I've done. Yeah, so here, where erbium, neodymium, and other elements, they have a lot of different energy levels, here we have nothing. So we are avoiding quite bad phenomena, I mean excited state absorption. For example, for erbium, if you are pumping erbium to this higher state, this excited ion, it can absorb another pumping photon and be excited to even higher energy state, and after it just goes to this basic energy level emitting green photon. So two pumping photons are in fact wasted for this green radiation, and this process can be quite efficient for erbium and other elements if we have nothing on these upper states here. Yeah, so we have this excited state absorption isn't possible in fact for the ytterbium. And also if you look at the pumping wavelength, yeah, the absorption is quite wide, and absorption can be made for this wavelength, so we can pump such a laser at this certain wavelength, and emission regarding these bands and this transition emission can be at 1 micron and slightly higher wavelength. So the efficiency of such a conversion is dependent on the difference in energy of the pumping photon and the emitted photon. For erbium, we are pumping at 980 and we have a radiation at 1.5 micron. Yeah, so by default we are wasting at least 33% of the energy for such a pumping. Yeah, this is some theoretical limit. If you consider pumping at 975 for ytterbium and emission at 130 nanometers, you can see this quantum defect. This is the name of this difference between the pumping energy and emitted energy. This quantum defect is much lower. It's way above 90%. Yeah, theoretical efficiency. And since for such a structure we have no other phenomena than stimulated emission, we have no excited state absorption and other things which are decreasing the efficiency. So optical to optical efficiency for such a laser or such an amplifier can be as high as 19%. Yeah, so these ytterbium doped amplifiers or lasers, they can be extremely efficient. In comparison, you have an erbium. The erbium, as I told you, this quantum defect is much higher, and also this excited state absorption, it takes a lot of pumping photons here. So the efficiency of the erbium is much lower. Even theoretical efficiency of such a structure cannot be higher than 50%. Even if you are using this pumping, the so-called in-band pumping at the wavelength close to 1.4 micron, because you can imagine we will have excited state absorption to this level and other not so nice phenomena here. Yeah, so to improve slightly the efficiency of these erbium doped fibers, some co-doping between with erbium and ytterbium is just performed for such a structure. So we can pump such active fibers using ytterbium ions as a pumping media, and then ytterbium ions are transferring the energy to these erbium ions and exciting the erbium ions. So this, if you are thinking about the high power fibers for 1.5 applications, you will surely meet these erbium ytterbium co-doped active fibers, not purely erbium doped, yeah, like for standard telecommunication applications, this low power, let's say, but for high power, practically only erbium ytterbium co-doping can be used efficiently. Okay, so right now we are after our normal time, so we can just finish for today. Yeah, so if you have any questions, of course, it is good time to ask. If not, thank you for your attention for today, and see you on the last, let's say, lecture next week. And after two week time, we will have a test. I need to think about we need to speak about having it remotely or here at the university, since you have another tests also the same day, and most of them are remotely made, as far as I remember, yeah? So, of course, I will match to other lectures and other tests you have for you to be able to join the proper test here or at home, depending on our, let's say, decisions we made.
All right. Thank you. Goodbye.
Bye bye.